Part 4, you will hear part of a lecture about how tree rings are used to study past climate. First, you have some time to look at questions 31 to 40. Now listen carefully and answer questions 31 to 40.
Today we are going to look at tree rings as a climate archive. The scientific study of dating wood by its ring patterns is called dendrochronology. It is used in archaeology, forest ecology, and climate research. In many trees, each visible ring represents one growing season. The tree produces different wood at different times of the year, and the boundary between one season's growth and the next creates the ring pattern that can be counted. The feature most often measured is ring width. A wider ring normally indicates that the tree grew more during that year, while a narrower ring suggests more restricted growth. The cause of that growth pattern depends on the environment. In dry regions, for example, wider rings often suggest greater rainfall during the growing season. The tree is not recording rainfall directly, of course. It is recording a growth response to favorable conditions. In colder environments, especially near the tree line or at high elevation, growth may depend more strongly on summer temperature. If the summer is too cool, the tree produces less wood, even when water is available. A key method is cross-dating. This means matching patterns of wide and narrow rings from different trees, so that the exact calendar year of each ring can be confirmed. Cross-dating helps researchers avoid mistakes caused by missing or extra rings. Researchers do not usually need to cut a living tree down. They can remove a narrow core from the trunk with a specialized borer. The core shows the sequence of rings while leaving the tree alive. Ring width is not the only measurement. In some studies, scientists also measure wood density, which can provide information about growth late in the season and may be especially useful in cool regions. Large data archives allow researchers to compare results across wide areas. The International Tree Ring Data Bank, for instance, contains records from thousands of sites, making regional climate reconstruction possible. The important point is that tree rings are a climate proxy. They are not thermometer readings or rain gauges, but natural records that stand in for direct measurements where instrument records are too short. Used carefully, they help extend climate history back many centuries. There are limits, however. A tree may respond to soil, insects, competition from nearby trees, or damage from fire, not just to climate. For that reason, scientists do not usually rely on one sample from one tree. They compare many trees from the same area and look for a shared pattern. They also choose sites where one climatic factor is likely to dominate growth, such as dry slopes where water is the main constraint, or cold upper slopes where heat is the main constraint. The method becomes stronger when tree ring evidence is compared with written records, modern weather observations, and other natural archives. In this way, tree rings provide a detailed but carefully interpreted record, especially for periods before systematic instruments were installed. Tree ring research is therefore both local and comparative. A single hillside can reveal how trees reacted to specific drought years over time, while a network of sampled forests can show wider regional patterns. The value of the method lies in combining biological evidence with careful statistical checking, so that a ring pattern is interpreted as environmental information rather than simply as an attractive line on a piece of wood in isolation alone.
That is the end of part 4.